Okay, I think we're live, but I require some kind of confirmation. Oh, I need to put this card in. There you go. Hey, John. And can you hear me? Okay. And this is good because this is a new computer. So, that's good. Video, no audio. Are other people getting audio? Is anybody not getting video or not getting audio? Audio bad, low quality, only coming from one speaker. Okay, good. Thank you. This is a new computer, and so I suspected this would be the case. So let's try to fix this. Audio, video, both, but the audio is only coming from one speaker. So I'll make it mono. Okay, so that should work. So now is it coming on both channels? Yeah. Moving in stereo. Yeah. Yeah, so it's okay. This is an absolutely brand new. Okay, good. Both speakers. Okay. This is a totally new computer. So I've got a new Mac Mini, and so Macs are pretty bad for streaming, for running OBS and such. So I had to set up a bunch of stuff. Okay, so is it still too quiet? Would you like it to be louder? Because I can make it louder. I don't remember my settings, but I definitely need to put in a plus dB. All right, let's do that. So let's go. Oh, I did it with a filter before, didn't I? Gain. Yeah, that's how we did this. Okay. Louder. Okay, here we go. So let's add a 10 dB gain. So that should be a little bit louder. Let's see if it looks louder to me. So we'll try out this level and we'll see if that works. I'm seeing it's starting to pop into the red now a little bit, so I think that's good. But I will still require your confirmation. I want everything to be perfect for you. Perfect. Okay. Okay, good. Better. Is it fine, or do you want it like a little bit louder? It sounds better. Okay, awesome. Hey everybody. Hey Europe. So why are the people in North America are gonna they're gonna try to go and watch their show tonight? They'd be like, what? Where is the show? What's going on? And that is because I'm now mixing things up to make versions of the live stream available to people who live in other time zones, because apparently we live on a globe. And so the time that we normally have been doing this since the beginning of time immemorial was that we would do the show at 5 p.m. Pacific time, which is great for me. That's like a perfect time for me, but it's not a great time for the people who live in Europe. And especially the two moderators who are mainly doing the work here, John Seffel and Zapfan, they have to stay up till 2 a.m. to moderate the show, and that's just brutal. So what I thought we would do is we're going to do one show a month that is for Europe. We're going to do one show a month that is for Asia, Australia, Asia, and then 2 shows a month that are good for me in Pacific time. And so we'll just sort of move around. And this one's great. Like doing the show that's good for the Europe evening. Hopefully you've gotten back from work, you're kicking back, you're eating dinner. This is the experience that the people who do the Pacific time show get to experience. But for you, you've got to be hardcore if you're going to watch it at 2 in the morning. So hopefully, this, oh, there you go. 3 for John and 4 for Zapfan. So hopefully this makes life better. Although Zapfan's busy, so just John is here. So the one that's going to be, so this is fine. 8 a.m. I'm a morning person. Like if I could do a 5 a.m. show and that would be fine. The one that's going to be rough is going to be the Australian one because it's probably going to be midnight or 1 my time to do the show. But I want to keep it consistent. Like I want it to be where you live, you get the show at your time zone in the evening at least once a month. And then, of course, obviously, for the folks who live in other in-between time zones, if you live in India, if you live in parts of South America, then, various times will be different for you. But hopefully everybody should be able to get at least 2 shows that are good for them every month. So this is the plan. John's on strike. Okay. All right. So for those of you who stumbled in, all of you new people who've never had been able to watch one of our live shows, this is the live question show. And this is where you ask me questions. I will answer them in real time, and then we will edit this down and we will turn this into our weekly question show. But now we're doing 2 question shows. But anyway, so the show's 2 hours long, and I have a hard limit. I've definitely got to go just a few minutes before because I have a meeting that I have to take right at the end. So the first hour is the part that gets recorded and is a little bit more formal. And then the second hour is a lot more casual. And so we will just hang out and we will chat. And that, we call that overtime. And sometimes that gets turned into other shows. Who knows? Now, the thing you should be aware of is, I have my 3 rules that I try to explain each time. So the first thing is I am a journalist, not a scientist. So, don't expect me to provide you with scientific opinions. I follow the scientific consensus and report on it. And I never stray from, except for a couple of things, which, are pure speculation. But in general, if you want my opinion of Penrose's cyclical universe theory, I have no opinion. I can tell you that people believe in it and other people disagree with it and what it is, but I will not, I don't have an opinion about it. I can't tell you whether it's a good theory or a bad theory. Just a journalist. The second thing is I try to give emphasis to the people who have never asked a question before. And since, hopefully many of you have never been able to watch the live stream before, we should get a pretty good following of people who've never had a question answered before. Now, that said, I am sort of thinking about the questions that we've had answered here in the question show over the last couple of weeks, and I try to not make it repetitive. And so, if I skip your question, if it looks like, hey, I got in early and I thought I asked a good question, it might be that we've answered that question many times in the last couple of weeks or months. And so I'm just giving that question a break. But in other cases, I don't know the answer. So don't take it personally. And whatever you do, don't ask your question a bunch of times. We got it. We got the one time. I've seen it. It's in the database. We've got John here. We've got John's robot buddy. And between the 2 of them, they'll be able to put those questions into the database that I use to check the question. So, all right. Thanks, everybody. Let's get started. Now, as always, I have some prepared questions beforehand, and then we will get into your questions. Okay. All right. New computer doesn't have Audacity. Oh, I'm sorry. Did you think this was going to be a smooth experience? No, this is, you get to be my guinea pigs. Just make sure that it's got the right device. It is this device, right? Yeah. Okay. Yeah, the keyboard is quiet. I'm not happy about that. I have a okay. I have a Apple keyboard. An old Apple keyboard. And this is the worst insult, is I am having to use a Mighty Mouse. This might be the worst mouse ever designed. I hate it so much. Trigger the right device. Yes. Okay. Yes, you can use the microphone. Okay. Just do this in mono. Okay. I think I got it. Yes, we are recording. Okay. Yeah, yes, that's the mouse that's impossible to use while charging. The charging port on the mouse is on the bottom, and so you can't use the mouse while it's charging. So if your mouse runs out of batteries, that's just too bad for you. All right, here we go. Thomas Shields. I don't think you answered Scott's question about the comet. He wasn't asking why do the tails and trails last for tens of thousands of years. He was asking why the comets themselves don't lose enough matter during their regular approaches to the sun or disappear sooner. So after a question show that we did, I guess last week, but I'm not sure exactly how many shows ago it was, but why don't comets run out of tail fuel, I think was the thumbnail that we had. And a lot of people in the comments said, you answered the wrong question. You answered, why do the tails last a long time in the solar system, but not like, how can the comets be continuously producing tails for long periods of time? And I apologize that I answered the question I wanted to answer, as opposed to the one necessarily that was being asked. And so here's the other version of that answer. So yeah, so comets, right? They come from icy regions of the solar system, and they are balls of a mixture of rock and water ice, as well as other volatile elements. And when comets get close to the sun, typically within about 2 to 3 astronomical units, yeah. When comets get relatively close to the sun, within the orbit of Saturn, Jupiter, they start to produce this tail that the solar wind that is striking the comet starts to cause the volatiles on their surface to boil off and create this tail that is following behind them in space. Now, the comet tail points away from the sun. And so that's why when a comet is moving towards the sun, it looks, it's got this tail going behind it and makes sense. But then when the comet is moving away from the sun, the tail is still moving away from the sun. It looks like the comet is following its own tail. But absolutely, this material is being degraded by the solar wind. And there's a limited amount of material that's on the surface of the comet. And it lasts somewhere on the order of thousands of years. And it really just depends on the orbit of the comet. And so in some cases, let's say you've got a comet like Halley's Comet that gets in relatively close to the sun, but then goes pretty far out into the solar system. Astronomers have been tracking Halley's Comet because it's a very bright comet. It's very recognizable for about 2,000 years, and it still produces a tail every time that it comes by the sun. But there are other examples of comets that maintain within the orbit of, say, Jupiter. They don't get that far away from the sun. And it appears that within just a few dozen orbits, they've lost their tails. They no longer have these volatile elements on the surface of the comet. Now, something that's really interesting is that over the last couple of decades, astronomers have found objects which are asteroids, and yet they seem to produce a comet-like tail, or a fairly diminished tail, but still. And so what's probably happening is that you're getting this loss of material on the surface of the comet, the stuff that the solar wind can easily reach. But then once that's all gone, you still got lots and lots of material that is underneath the surface, but now it's all just covered in this shell of rock. And so if something happens, like the comet gets hit by an asteroid or breaks apart in some way, then all of this material is then freshly revealed to the solar wind, and then it can generate a tail again. So comets definitely don't last forever. They last a few thousand years, depending on their orbit, how close they get to the sun, and how far away they are from the sun at the farthest point of their orbit. If there's like a third version of this question, I'm ready. Oh. This is for you, Chad. Okay. Okay. JDMM4UB. How come there are so few pictures from the Milky Way taken from the space station? I think they'd have a much better view than we do on Earth. The astronauts on board the International Space Station absolutely have a better view of the Milky Way than what we have down here on the surface of the Earth. They are above the atmosphere, and so they get this clear view. They're effectively, their eyeballs have become space telescopes, and they're able to look out into the cosmos. And I've had a chance to interview astronauts directly about this question, especially the ones who are amateur astronomers. I talked to Ron Guerin and Don Pettit. And Don Pettit actually is on the International Space Station right now, although, we were having a beer at a conference and not, talking to him on the station. And what the impression I get from them as amateur astronomers, like they own telescopes, they go out, they do photography of the night sky, that the experience of being on the International Space Station is like you're being in the darkest skies you've ever been in on Earth, and then some. And that in fact, it's actually a little disorientating because just the regular stars are all so bright that it's really hard to orient yourself, to recognize the constellations, because just more and more stars are out there. And if you've ever been in really dark skies, you've experienced a version of this where there's so many stars and they're all so bright that you actually can't find the obvious constellations that you're very familiar with. But the Milky Way apparently does look amazing. And so, why are we not seeing a lot of images of the Milky Way taken from the space station? So there's a couple of reasons. One is that the space station orbits around the Earth every 90 days. The space station orbits around the Earth every 90 minutes. And so it's in the sunlight, and then it's in the shade of the Earth, and it's in the sunlight, it's in the shade. And so if you have cameras sitting outside that are attempting to do astrophotography, they're going to, for a time, be in complete sunlight, and they don't like that. And so you're going to need to switch the cameras on, switch the cameras off, and so on. Also, a lot of the cameras, like the automated cameras that are on board the International Space Station, are pointing down. They're looking at the Earth. In some cases, they do actually get like a nice view off to the horizon, and you can see the curvature of the Earth, and then you can see the sunrise over the horizon and things like that. Now, there were a bunch of automated cameras installed on the space station, and there are still some, which take pictures in different angles on a regular rate. And a lot of people made really cool time-lapse videos of the Earth passing under the space station. You could see auroras forming, and then it was in day, and then it would go into night, and you could actually see the Milky Way rising above the limb of the Earth. And then the other thing is that when you do have an astronomy-minded astronaut on board the station, they've got a bunch of cameras at their disposal. And Don Pettit is up there right now and, has talked quite a bit about how he takes pictures from the cupola, which is this cool observing room on the space station. And he has taken just amazing pictures of the Milky Way seen from the space station when it's in one of these shaded periods. And so hopefully, Chad's been putting up a whole bunch of really cool images of the Milky Way seen from the space station. So it's just like most of the time it's looking down at the Earth during the day, or there's images of the astronauts inside the space station. It just has to be like an astronaut has to decide that they're going to go look through the cupola, point their camera, take images of the Milky Way or the moon or other things that are going on. But there are tons of those pictures and even time-lapse videos of it. Did we get that? Yeah. IARC-SIM. In 5 billion years, the sun will go through a giant phase and expand around the Earth and the moon. Won't the Earth and the moon get dragged so close to the sun by friction with the sun's gases that they won't meaningfully exist in 50 billion years? So that 50 billion years number was from a previous show where I said what the time it would take for the Earth and the moon to tidally lock to each other, to become a true double locked planet. And so a good example of this is Pluto and Charon. So in the case of Pluto and Charon, Pluto is locked to Charon and Charon is locked to Pluto. They are both gazing at each other as they orbit around a common center of gravity between the two of them. And with the Earth and the moon has locked to the Earth, but the Earth has not locked to the moon. And so because of the way the tidal forces work and the conservation of orbital momentum, the Earth's rotation speed is slowing down and the moon is moving farther away. And eventually the Earth will lock to the moon, but it'll take about 50 billion years. And I think I even said in the question that, it doesn't matter because the sun will be dead by then. And so, yeah, around 5 to 7 billion years from now, the Earth, around 5 to 7 billion years from now, the sun will bloat up as a red giant as it uses up all of the hydrogen fuel in its core. It'll become this red giant. It will consume Mercury. It'll consume Venus. But astronomers aren't entirely sure that it's going to actually consume Earth and the moon. And this just goes back and forth. 1 week we'll report on Universe Today that someone's produced a paper that says that the sun is going to consume the Earth, and then someone will produce a different paper that says that the sun won't consume the Earth, and we don't really know. And the question comes from the mass loss. So as a star like the sun, a main sequence star, gets into that red giant phase, it starts to, it bloats up, and then it puffs out these outer layers and then shrinks back down and loses some of its mass. And then it does it again and then keeps going back and forth. And each time it sort of throws this shell of material out into space. And eventually it ends up losing whatever mass that it does. And so the mass loss will cause the Earth and the moon to change in their orbital position. And it might very well be that, that the Earth will orbit a little more closely to the sun will bloat out, and it will actually get captured by that red giant phase. Or maybe it won't. And so, this is one of those continuing unfolding mysteries. And maybe we're just going to have to wait 7 billion years to find out what happens. But whatever the case, the solar system will be unrecognizable in 50 billion years on that final day when the Earth has finally tidally locked to the moon, or both were long gone, gobbled up by the sun. Okay, so those are all the prepared questions that I had, and so now we'll get into your questions. Look at all these people who've never had a question answered before. This is delicious. John Muzz, have you ever approached Jim Al-Khalili? There's an interview on my channel with Jim. Maybe it was for the Weekly Space Hangout. I think it was on this channel. Sorry, just looking through all of the cool questions. Kyle Stedward had a random thought. If you could orbit right on the edge of an event horizon and then have a long pole and put the pole through the event horizon, what would happen? So the question you're asking is that if you were orbiting around a black hole and you're right at the edge of the event horizon, this place where the escape velocity of the black hole exceeds the speed of light, and then you took a pole and you put the pole down into the event horizon, what would happen? So, like, obviously the first thing is like, what is the tensile strength of the pole that you are using? Because it needs to overcome just immense tidal gravitational forces that are going to tear it apart at an atomic level. And no matter what the pole is made of, it is going to be just pulled apart, and you're not going to be able to bring anything back up. But I'm assuming that you have created this pole out of some sort of unobtainium, something that is so strong that it can never be. Maybe it's made of black hole, maybe it's made of neutron star, or even tougher than that. It cannot be shredded by a black hole's tidal forces. And so you kind of then have to go back to the first rule of the event horizon, that nothing, not even light, can escape its grasp. And so there is no amount of force that you could put onto that pole to try and pull it back up that would allow it to escape the pull of the black hole. Once you're inside the event horizon, all paths lead to the singularity, including the pole. Now, obviously it's going to pull you in with it. So, but you can't break the rule, which is you can't get out of it. Even if and because the pole strong enough to handle the tidal forces is impossible, that alone will make the problem not work. So even if you could, you can't get it out. Like it will be held fast. Graham Goins, when did the universe become our universe in a greater universe? Well, I mean, we don't really know what caused the universe, but essentially, by the best measurements that astronomers have been able to make, the observable universe that we find ourselves in today has been around for 13.8 billion years. And so right now, we can look to the left of us 42.5 billion light years away. We can look to the right of us 42.5 billion light years away. And 46, right? We can look to the left of us 46 billion light years away. We look to the right of us 46 billion light years away. And yet in the past, those regions were 20 billion light years apart. And then at one point they were, just a few 100,000 kilometers apart. And then there was a time when the entire observable universe, everything we could see, was the size of a volleyball, and maybe smaller, maybe the size of a pea. We don't know, or maybe like a singularity, infinitely small. But that was just one component of the larger universe. And so, if you had this volleyball-sized version of the universe, then right beside of it there was another one, and so on. And so the question that you're getting at is like, what came before, right? Like, what was the environment of the universe that then we got our local version of space starting to become less dense over time and become the universe that we see today? And, obviously you can think, well, okay, there was another version of our universe right beside us, and they're going through the same thing that we are. And then there's the people that kind of split the difference, right? The people who are in between us and the universe beside us, and they've got their own sphere, and they're seeing a little bit of our universe and a little bit of the next universe. And so, it's thought that the universe, if the universe is infinite today, if the universe is infinite, one more time. If the universe is infinite today, then it was infinite before this de-densification started to happen. But like, what set this off in the first place? And, we don't really know. In fact, we don't know at all. And anyone who tells you doesn't know. They're guessing, or, someone told them, or, they've got a theory, but they don't have any observational evidence to back it up. But probably the strongest theory that's going right now is this idea of inflation, that there are problems with the Big Bang. in the flatness of the universe, the lack of magnetic monopoles, the way that parts of the universe shouldn't have been able to sort of average out their temperature, and yet they did. And so this idea of inflation, that before we got just the regular de-densification of the universe, there was this period that was sort of incredibly short, like a fraction of a second, where the universe went through this doubling in size. And sort of one of the interesting things about, the underlying requirements for this idea of inflation is that it was going across a larger volume of space, and that different parts of this universe were inflating at different times and different speeds. And it could very well be that there are parts of the universe that are still inflating today, billions of years later, and other places where inflation stopped before we did. And that in each one of these local areas of the universe, they potentially have their own underlying laws of physics. And you can imagine, each one is gone off and inflating in its own place and pushing the other universe parts away from them. And we could never reach one of these alternative universes. So one possibility is that just the entire universe is just getting less dense over time. One possibility is that there's sort of this larger landscape of universes within the universe, and they're sort of experiencing different versions of themselves, and they're not going to overlap. So, we don't know. We don't know is the answer. And that's got to be fine. Like you've got to be okay with the possibility that we may never know the answer to this question. A million years into the future, our descendants will go, where did the universe come from? And the astronomers will go, I don't know. We've looked for a million years for any shred of evidence that connects this universe to what came before, and we haven't been able to find anything. And so everything is still on the table. We still don't know. And hopefully in a billion years, the astronomers then will have a better answer. Jamie Orlando, how can Venus hang onto its atmosphere without a magnetic field? So here on Earth, the magnetic field is very helpful for keeping the lightest elements in our atmosphere, the hydrogen. But still, like, Earth is losing tons of hydrogen and other light elements to space because of the solar wind every year. And in fact, like the mass loss from atmosphere roughly matches the amount of additional mass that gets added to the Earth from meteorites and stuff landing, dust hitting the Earth and getting added to our mass. But that's a totally different conversation. But the question you're asking is, well, okay, so Venus doesn't have a planet-wide magnetosphere that is protecting it in the same way that Earth is being protected. Mars doesn't have a planet-wide magnetosphere, and Mars lost most of its atmosphere. So why doesn't Venus lose its atmosphere? Now, I mentioned that the thing that you're losing is the lighter element. Hydrogen is the lightest element. It is the trickiest element, and it really wants to escape and get away. And so you've got this ultraviolet light that is coming from the sun. It is breaking up molecules in the atmosphere of Venus. The hydrogen is escaping out into space, being pushed away by the solar wind, and it's concentrating the heavier things that you get: carbon, oxygen. And so you've got a very thick atmosphere of carbon dioxide on Venus. It is losing atmospheric mass. There is a tail of material that is coming off of Venus. It's just that it has so much material available that it's just going to take a long time. There's more nitrogen in the atmosphere of Venus than there is in the atmosphere of Earth. And yet our atmosphere is, 70% nitrogen? So there's just a lot of atmosphere at Venus for it to lose. Definitely double check that, Chad. That was out of memory. Okay. Licod. M. Licod. Do you think, given the current geopolitical climate, there is a chance in the next 5 to 10 years for a rise in interplanetary missions, or will there be cuts? So I'm recording this episode in the beginning of December 2024, and the answer is that we have no idea what's going to happen in 2025 when the Trump administration takes over the presidency, when you've got a House and a Senate that's aligned with Trump, with a Supreme Court that's aligned with Trump. Now, in general, space exploration and human space exploration and even science are like politically neutral. That often people from across the aisle will come together to fund and support space exploration programs. And so for a lot of stuff, it's very clear what's going to happen to programs under the new administration. But in the case of space exploration, we don't know. And at the same time, there's a lot of space exploration that is happening from around the world. And so, the simple answer is we have no idea, right? The more complicated answer is why don't we look at the rest of the world first, and then we'll come back to the United States. Obviously, they're a big player. And so China, for example, is just moving as quickly as they can to establish a presence in the solar system. They've got a space station that they've launched and are adding modules to it. They're going to be adding a space telescope that's going to fly close to it very soon. They've been retrieving samples from the moon. They're planning on having humans set foot on the moon by 2030. And so you can imagine, let's say 2030, the United States has deorbited the International Space Station and has not built a replacement and has not completed building the Lunar Gateway, or maybe they cancel Lunar Gateway. We'll get into that in a second. Then the Chinese are the only people with a space station in orbit, and the Chinese are going to have humans setting foot on the moon. They're also planning their Mars sample return mission, and this is something that NASA looks like they're canceling or are going to come up with a new way for the Mars sample return mission to go forward. The Chinese are planning to send their mission in 2031, and we'll probably see the samples back on Earth 2033. And then you've got the Indians, and India has been putting a lot of energy and investment into their human spaceflight program. It's expected that we're going to see people from India go into orbit before the end of the decade, and they're probably going to build their own space station shortly after that, and plans to send humans to the moon as well, which is really exciting because the Indian space program is very innovative, and they're making great strides. So definitely watch what they're doing. Europe is very tied to what happens with the US. There's a lot of missions that they work on together, like James Webb. In fact, when the Russians invaded Ukraine, the NASA pitched in on the Rosalind Franklin rover to help sort of get that mission to Mars. So you see a lot of collaborations between Europe, and they have no sort of separate plans, although they have plans in the works to develop a lunar village. So who knows what the sort of the future of human exploration of the moon looks like from Europe. And so the big question, of course, is the US. There are a bunch of missions that are already on their way, right? We've got the launch of Europa Clipper, the launch of Psyche. Like, these spacecraft are already in space. Then you've got missions that are in the final stages of being completed. So you've got, say, the Nancy Grace Roman Space Telescope, which is going to launch in 2025. You've got Titan Dragonfly, which is going to launch in 2028. And then you've got longer science missions, which are still in the planning stages. Things like the Habitable Worlds Observatory, which probably won't launch until the 2040s. And so you need this sort of continuous funding for these projects. And then sort of the elephant in the room is what's going to happen from the human space exploration side. Right now, NASA is stacking up the second Artemis mission, the space launch system built by Boeing. These things cost $4 billion a pop. And in theory, in 2026, this rocket is going to fly and do a flyby around the moon and come back. No, 2025? Anyway, yeah, 2025 and then 2026. Anyway, in very soon, Artemis 2 is going to do a flyby of the moon with 4 astronauts on board. And then following that, you get the launch of Artemis 3, which hopefully is going to have human set foot on the moon before the end of the decade and before the Chinese are able to complete their first mission to the moon. And so the question is, like, what could get cut, right? Like, on the one hand, you could imagine the sort of the cuttiest scenario where science programs are cut, where the Space Launch System is canceled, where exploration is then contracted out to various private contractors like SpaceX. You could imagine a situation where things go essentially as they had before, because there's a lot of political will. There's a lot of employees across tons and tons of different parts within the United States that are all depending on the Space Launch System and the current ways that we're flying in space, as well as the science and the missions and the development and all the contractors. Like, there's a lot of momentum in the current way things are done. And then what will probably be the most likely is that you're going to see priorities change. You're going to see some missions cut. I would be shocked if the Space Launch System survives another administration. Even if it does work and it does bring humans to the moon, it's incredibly expensive, and there should be less expensive ways to accomplish this. So this is a very long-winded way of saying that, for the rest of the world, they have their plans pretty solid. The US, everything is in flux, and we can have this conversation a year from now, and I'll be able to report on what happened. And until then, just watch, and I'll let you know what actual concrete things happen. Leafbinder. Fraser, have you thought about going on Joe Rogan's show to bring awareness to astronomy? I haven't been invited. Oh, I hate this mouse so much. There you go. So Nick Cooper, you ask a bunch of questions about my opinion. Is energy matter eternal in your opinion? Just a journalist, not a scientist. I have no opinions. Tony Hobbs, if Sagittarius A star suddenly became an average luminosity quasar, would we see it from Earth? And if so, what kind of brightness would it have? So, all right. The supermassive black hole at the heart of the Milky Way, Sagittarius A star. This is a supermassive black hole with 4.3 million times the mass of the sun. 4.1? This is a supermassive black hole with 4.1 million times the mass of the sun. And it is not a quasar. A quasar is when a supermassive black hole is actively feeding, materials falling into it, it is blasting out all of this radiation, and it is visible. These are the brightest continuous objects in the universe. We can see quasars from billions of light years away, times just after the beginning of the universe. And yet we can't see the galaxy that's around them. We can just see the quasar. And so the Milky Way and most galaxies no longer have a quasar, but it might have been that the Milky Way had a quasar in the past. And the best chance for the Milky Way to get a quasar in the future is when Andromeda crashes into the Milky Way, or I guess Milky Way crashes into Andromeda. Anyway, when the Milky Way and Andromeda merge, then both the black hole at the heart of the Milky Way as well as the black hole at the heart of Andromeda will start feeding. They will get material, and it's entirely possible that they will turn into quasars. So what would that look like from the Earth? You're standing here, you're looking towards the center of the Milky Way. What would you see? You would see nothing. There is an enormous amount of gas and dust that is surrounding the area, and astronomers call this the zone of avoidance. And that dust is so thick that if there was a quasar at the heart of the Milky Way, you wouldn't see it because the dust is obscuring your view. But what if there was no dust? What would you see? You would see nothing, in that the quasar would not be pointed at you. The quasar would be pointed at some other direction in the sky, and so it wouldn't be a very bright object in the sky. I think I did a video about this many years ago, and I think the agreed brightness is like magnitude 8. So if you had a reasonably good telescope and you knew where to point it, and you had somehow removed all of the dust from the center of the Milky Way, then you would be able to see the quasar, but it wouldn't be that bright. Now, if it was pointed directly at you, which would be very weird because it should be aligned with the galaxy, but if it was pointed directly at you, then it would be brighter. But still, if and when the Milky Way gains a quasar in the future, billions of years from now, people on Earth won't be able to see it. Zero Cool, what recent research have you heard about the attempts to unify gravity with the standard model? Any new ideas or breakthroughs gaining attention? Nothing. Nothing that is, there's a lot of standard blue quantum gravity, string theory, the same kind of ideas, and nobody's really making any progress or headway. Coho Bunny Music. So where does Mr. Cain get his questions? Only paid stuff on Patreon? You just asked your question. That was your one question, and that's what you asked? No, you can ask as many questions as you like. But I think it's always funny when people in the comments, they're like, where do I ask questions? Like, you just did. You did it. Ooh, good question. Jesse Ray, I've been thinking about contacting my local town to see if I can convince them to take some steps to reduce light pollution. What are some things you would do or recommend if you were in my position? Light pollution is a scourge on our planet. And when you think about it, almost half of humanity can no longer see the Milky Way from their backyard. That most people who are watching the show, especially if you're in Europe, there's very few places you can go in Europe where you can actually see the Milky Way because of the light pollution from the cities. And I think that's a tragedy. And it doesn't have to be this way, that there are places in the US. I was in Tucson, and they have a really amazing dark sky ordinance for lighting. You have to use certain kinds of LED lights. You have to point them at the ground. There are places near Flagstaff where it's even more extreme because there are all these big observatories that are nearby. And they take the night sky very seriously. And it is possible to make a place that feels safe, lit as you walk around, and yet you're not pointing all of this sky, lights up into the sky for sky glow. So what are the recommendations? Well, there are some really good recommendation lists from the International Dark Sky Association, and they provide the kinds of information that you're going to need to take to your local town to try and convince them to put in those kinds of ordinances. But in general, it is to point your lights, use directed lighting, so you're pointing it down at the ground in the places where people need to be able to see things, and not unidirectionally, and definitely not up into the sky. to turn them off and on at times that make a lot more sense, and to use a color spectrum that is better for the eyes, better for astronomy, better for seeing the night sky. And it's really nice. Like, I've been in places where the lights are low, but they're pointed at the ground and you can still see everything. And yet you can also look up and you don't lose your night vision, and then you can see the Milky Way above. And so it is definitely possible to be able to do that. And I think just like anyone who's watching right now, if you're part of a local government, if you want to try and make a change to bring astronomy into the reach of more people, this is the practical thing to do. And I always find it really funny because people are so mad about how satellites, potentially, the mega constellations, are going to be causing problems with the night sky. And they are, like, no question, they are going to be causing light pollution, this kind of general sky glow. But it is, it doesn't hold a candle to the light pollution that has already happened from people pointing their lights up. And we got these lower power LED lights, and the thought was, okay, that's going to bring light pollution down. But in fact, with the rise of LED lights, light pollution has gone up, that people are using the power savings to just put out more lights and cause more sky glow. And this is all moving in the wrong direction. So get involved. Find out where your nearest dark sky preserve is. Go see what the Milky Way is supposed to look like. Go check out the International Dark Sky Association, find their recommendations, and then bring these issues up with your local government. And I think most people love space and would love to be able to see space better. And, a lot of times it's never occurred to them that these are things that we could restore. So good luck. We're at 52. Okay. Skuckix23. Isn't the crisis in cosmology a blessing? Both types of measurements should be accurate, but they don't overlap. Isn't this the best pointer for scientists on what to look for? Yeah, the crisis in cosmology is a terrible name because crisis feels like it's a thing that's bad, right? That, oh no, there is this crisis that if we don't solve this problem, then the universe will be destroyed. Cosmology will cease to exist. But it's nothing like that. It's that on the one end of the spectrum, when you measure the distance to Cepheid variables and you measure the distances to type 1a supernova and you use that to calculate the expansion rate of the universe, you get one number with a error bar of, of a certain size that you're comfortable with. And then when you measure the same kind of thing, but now you're measuring from the cosmic microwave background radiation, which is the oldest light in the universe, you get a different number. And the numbers are very close. And it used to be that their error bars overlapped, and so people assumed, okay, it's some number in between. But now the error bars no longer overlap, that both are so precise, and yet they are not the same answer, that this has caused the Hubble tension, the crisis in cosmology. And this is incredibly exciting, that this is the kind of thing that most scientific fields would just love to have this problem, because you're exactly right that because you have different methods of measurement giving you different answers, then you can start to track where this divergence started to happen. Why is the change in the expansion rate of the universe happening over time? Why was it different in the beginning than what it is now today? And then the possibilities are that it's measurement error. And, some of the best people in the world are working on this question. I've got an interview with Adam Rees where we talk about the level of effort and energy they've gone into to confirm the Cepheid variables. And most recently, he's then gone on and confirmed the type 1a supernova. And then you look at how exquisite the measurements to the cosmic microwave background are from the Planck mission, that this is all going really well. And fortunately, there's a lot of really cool new surveys that are coming up that are participating in this. So for space, you've got the Euclid mission, which the European Space Agency launched a couple of years ago, and we got some initial data from them, but we're still going to be a couple of years before we get their full data set. And they are measuring. They have sort of two instruments on board Euclid. One is to measure with visible light. They're measuring the shape of galaxies, and they're using that to try to see the amount of gravitational lensing that is happening to these galaxies over time. Where is the mass distribution over time? And then the other thing is they've got an infrared instrument that allows them to measure the chemical composition of the galaxies. That helps them figure out how far away they are moving away from us. This is going to be supplemented by the Nancy Grace Roman telescope, which launches in 2027. And then we've got Vera Rubin, which comes online in just a couple of months from now. And it's going to be measuring type 1a supernova happening across the universe, things like that. And then something that you're going to start hearing a lot in the next couple of months, we're going to do a ton of reporting on this, is there's the DESI survey, the Dark Energy Survey Instrument Survey. And this is very similar to what's being done with Euclid, this measurement of the sort of the expansion of the universe, the distribution of dark matter, dark energy over vast periods of time. And you're seeing some really interesting results that are coming out of it. Like, people are seeing support for the idea that there's some connection between black holes and dark energy, although other people are very skeptical, and it's a very out there idea, and yet there is some kind of correlation. You're seeing very good tests of modified Newtonian dynamics, this alternative theory for dark matter called MOND, and the news isn't good. MOND is probably going to lose favor with the astronomical community based on the DESI survey. But again, this is all very new. And so it's this sort of vibrant time of a lot of really interesting ideas and the observations that they can use to back up the various theories that they have for what's happening in the universe. And so as a journalist, it's like, I don't know, I'm trying to think of a sports metaphor, but it's like the Super Bowl. There's something really exciting going on right now, and there's a lot of really interesting, meaningful progress that's going to happen. And so for you watching, I hope you really enjoy it, that I hope you will, you understand the mystery, you appreciate the different ways to try to explain it. You're going to watch as each of those different methods is attempted to try to make some kind of progress. You're going to see as the scientific consensus comes together on what appears to be the answer that best matches the evidence that's been found so far. And then you're going to see, hopefully, what were mysteries in the past start to become understood, and yet you're going to see more questions pour out of that. And so that's the scientific method. That's why I find this also entertaining. And this is going to be one of the most entertaining things that I think we can all watch in space and astronomy. Okay, so that's the that is entered. So that's the regular show. Now let's switch into the overtime show. And I think I'm just going to keep it rolling. I think that's what I'll do. Okay, all right. So normally, in the olden days, I would do a bunch of administration stuff at overtime, but now I don't do that anymore because we break the show up into two pieces and we have to do some coordination. So I'm just going to go straight into overtime. Okay. Something right on the... Okay. Birds adorb. Why can't there be a telescope constellation around the Earth to do more science and look for space objects? Oh, is this is in the field? Just barely. Okay, all right. Birds adorb. Why can't there be a telescope constellation around the Earth to conduct more science and look for space? So like, I'm trying to think of a good way to go into this. Okay. So in general, there's no reason why a constellation would be more advantageous than one space telescope. When you think about, say, the Hubble Space Telescope, it is orbiting around the Earth every 90 minutes, and it is able to focus on one target. Depends on where the target is. Sometimes the Earth gets in the way, and so it can only observe for half of its orbit, and then it has to wait, and then it can observe for half of its orbit. In other cases, there are objects that the Earth isn't getting in the way, and it can make its observations for the entire time. And so if you're going to have a constellation of telescopes, then they're going to need to do something that makes this combination of telescopes more effective. Now, there have been plenty of examples where constellations have flown. So, for example, there's a mission called Cluster, where there were Earth observing satellites that were flying in a train, closely following each other, and they were communicating with each other. And as they were going over Earth's lumpy bumpy gravity field, the distances between the satellites was changing, and that allowed them to map the position, the sort of the shape of the Earth's gravitational field, and that you need to have the separate satellites. There's an upcoming mission called LISA, the Laser Interferometry Space Antenna, and this is going to be measuring gravitational waves. And same thing, you've got 3 satellites that are in this triangle shape, and they're communicating with each other, measuring the distance to each other. And then as soon as a gravitational wave passes over the LISA satellites, it changes the length of the legs of the triangle, and then they're able to measure the gravitational wave that came by. The thing that would be incredibly useful for a space-based telescope is an interferometer. And so we have examples of these here on Earth. There's the Very Large Telescope, and there's the Event Horizon Telescope, which was this collection of radio telescopes around the entire planet, which working together were acting as if they were a telescope the size of planet Earth. And so the cool thing about telescopes is that if you separate the telescopes and you observe at exactly the same wavelength of light, then you get a telescope that acts as big as the size of the gap between the telescopes. And so if you have 2 Hubble Space Telescopes and you put them 100 meters apart and they observe the same object and you synchronize their time, it's as if you have a telescope that is 100 meters across in terms of its resolution. And that would be amazing. But technically, having those 2 telescopes be able to observe right down to the individual wavelength is just incredibly difficult. And so a thing that we're going to see in the next coming decades is various attempts to fly interferometers, constellations of space telescopes that will, start to act like larger virtual telescopes. So it's just really hard. Oh, is it Swarm? Yeah, not Cluster, Swarm. So we're in overtime. Okay. And Ian Kumar, you asked the same question, so there you go. I don't know, BIN. I don't know what the acronym is. Is there a plan or design for a solar system internet to replace the deep space network with something more robust and useful for colonies or data-heavy science facilities? No, there is no plans to replace the deep space network with a space-based infrastructure with various relay stations to support the thriving colonies on Mars. And that's because there are no thriving colonies on Mars, that we are decades away from thriving colonies on Mars. And that if you do get the thriving colony on Mars, then building the satellite uplink to support their communications is relatively easy compared to how hard it was to get a self-sufficient community on Mars. So there's a lot of really interesting upgrades that are happening to the deep space network. And I think I covered this in a recent question show that, it's oversubscribed, that to communicate with all the different spacecraft out there, there's not a lot of room on the Deep Space Network. But with the Psyche mission, they're actually able to communicate with the spacecraft with a laser, with an infrared laser, and they're able to get dozens, maybe even more than 100 times as much data back and forth from the Psyche mission. They're able to send, ridiculously high bandwidth cat videos, photos, things like that. And you're going to see these installed by default on all spacecraft in the coming decade. And so you're going to see much faster, much better, reliable communication with spacecraft with a lot less infrastructure. And the thing that then would take that to the next level is to set up relay stations. That you've got things at Mars, you've got things in the asteroid belt, you've got things out at Jupiter, big transmitters that are able to collect the communications from nearby and then beam them directly back to Earth. And that just, we don't have the need yet. So right now, the Deep Space Network is all that's required. Captain Butt, given a vehicle with unlimited omnidirectional thrust, could we eliminate all frames of motion and fall towards the center of the mass of the universe? No, there is no center of the universe. There is no center of the mass of the universe. That you are experiencing the combined mass of every object in the observable universe. You're experiencing the gravity from the sun. You're experiencing the gravity from the Earth. You're experiencing the gravity from Jupiter. You're experiencing the gravity from Alpha Centauri, from Andromeda, from a quasar seen 1 billion years after the Big Bang. If it's in the observable universe, you can both see its radiation and feel the effects of its gravity. And there's no center of this mass. It is distributed across the entire universe. And the reality is that you're experiencing most of your gravity from the Earth because you're very close to it and it's very massive. And if you got out of orbit around the Earth, you could get to a place where you're balancing the mass between the Earth and the sun. But I can't imagine how you could go anywhere where you could balance the mass or balance the gravity from all of the objects that are interacting, because they're in many cases going to be interacting in opposite directions. Orlando Erickson, is there a structure for planet types for exploration? Orlando Erickson, is there a structure for planet types for exploration? Something that we could translate into types of vehicles, helicopters, rovers, submersibles. Right now, almost all of the exploration of other worlds has been done with either landers or rovers. And, obviously there are multiple rovers on Mars right now. There've been 5 rovers over time, 6. So you've got the initial one sent by NASA. You've got Spirit Opportunity. You've got Curiosity, Perseverance, and then the Chinese had their Tianwen, rover, and then Perseverance brought along a helicopter, and that was sort of the first new method of exploring that's ever been tried. And you're going to see sort of different versions of these kinds of body plans working in different places. So, NASA is working on the Titan Dragonfly. It's going to launch in 2028 to go to Titan. It's going to fly in the atmosphere of Titan. Flying objects are going to work pretty well at Venus. And you can imagine, say, balloons or dirigibles working at Venus, as well as that working at both Mars and at Titan. Helicopters will work on Mars and Titan. Helicopters won't work so well at Venus just because you're going to crash, but airplanes might work. So there are like solar powered aircraft that can fly continuously forever. And so as long as you can stay within the sun on Venus, you could probably fly this aircraft. Airplanes will work on Mars as well, although they might have to land every now and then to recharge their solar panels. But then there's a lot of really other interesting ideas. Submersibles, right? Like you go to Europa or Enceladus or Pluto, drill down through the ice and then swim around inside the water. There's snake bots, which are sort of similar to snakes, that they can crawl into hard to reach spaces. There are walking robots that have been proposed, jumping robots, places like the moon or asteroids where the thing can jump for tens of meters, or in the case of an asteroid with very low gravity, it could travel halfway around the asteroid and land again. So there's a lot of really cool ideas. Tank tread type rovers as opposed to wheeled rovers. So, as we, right now, the terrain has been chosen because it's very safe. But in the future, a lot of the most interesting places are the places that are unsafe. And those are the places that we're going to want to go. So stay tuned as we see interesting rover ideas finally get deployed off-world. Noor Ahmed, what tools that don't exist yet could make space science journalism more accessible or preferable for people? Like, what could make it objectively easier to get fair and accurate information? I don't think that there's anything out there that needs to be developed that doesn't exist right now. There are a lot of really great, dedicated space journalists who have focused their careers on just reporting space and astronomy. There's all the people who work at Universe Today, of course, but then there's our competitors, right? Space.com has a lot of really great reporters, Space News, and then there are people who do good space reporting for larger groups. So Eric Berger at Ars Technica, people who work for the Houston Chronicle. So there are, there's a lot of dedicated space journalists. And if you go to places like Twitter or Blue Sky or Mastodon, you see a lot of these people are doing a lot of posts and interacting. And the other thing that's really cool is you've got people who aren't journalists, who are actually the scientists, but are doing a really good job of outreach in various communities. And so, again, like Blue Sky is the one that I'm pretty excited about right now, just because I see a lot of the scientists who are doing like really great posts there. And so, but there are some lists of people that you can follow who are, people like me would recommend, and as being reliable sources of scientific information. And then you can follow that and get this feed that's filled with cool explainers and interesting information. So, I can imagine that artificial intelligence can go horribly wrong, or it can go horribly right in the future, where, on the one hand, you've got the AI slop that's being produced where people are taking, they're asking important questions to AI and it's producing this low grade, incorrect information, and they're posting it everywhere they can. And it drowns out journalists who are putting in the hard work and double checking their information and checking their sources and so on. But you could go the other way, which is that, I've done some experiments with AI where I've, say, taken an article that I wrote and fed the AI the source material, the paper that I'm writing on, and then ask it to go sentence by sentence and fact check my article. And found lots of mistakes that I had made, that where I maybe hadn't phrased things very well, or there was ambiguity, or I had gotten the number wrong, or that kind of stuff. And so you can imagine this other world where the AI gets really good and is able to provide this really hardworking, reliable, fact-checking service that allows you to create more useful, more accurate information. And so I think we're going to do one then the other, which is we're going to go through the AI slop period where the AI is going to really make a bad name for itself and everyone's going to be really disappointed at what the AI can do. And when they see that there's AI baked into some product, they're going to not want to use it. And then you can imagine this other version down the road where people are like, AI comes around and it no longer hallucinates and it's actually reliable and improves the work that we do and can even filter out the AI slop that was produced in the days of yore. And so maybe we'll get to a place where it's actually useful. So I think that's probably the future that we can hope for, the best future. But until now, like, I think the thing that you need to do is find sources of information that you find credible, that you can trust, that they appear to be giving off all of the right signals, that they are focused on the scientific consensus, that they cite the sources that they use for the work that they do, and trust in them to give you an unbiased view of what's going on with space astronomy and just science in general. One plot African crawl. We humans have great experience in living and working with the space station. Do you think that our best chance of exploring other planets and moons is not to land on them, but to orbit them? Yeah, I had a poster that I used to have. I should put it up. It's going to probably go back there. This says gravity wells are for suckers. And so part of the problem with us exploring places like Mars is you had to get off of the surface of the Earth. You had to do 7.5 kilometers per second of escape velocity to get off the surface of the Earth. You then have to escape Earth. It's like another 5 kilometers per second. 8 kilometers per second. You have to go to Mars. That's more delta V. And then you enter the atmosphere, land on the surface of Mars. And then if you want to go back into space, you have to escape that gravity well. And so why do all that when you can just fly off of the surface of the Earth and go into orbit and, take advantage of being in space without having to then, drop back down into another gravity well? And there's like a couple of really big issues. One really big issue with us setting any kind of permanent inhabitation on the moon or Mars, and that is the low gravity. On the moon, gravity is 1/6 of what it is on Earth. On Mars, it's 1/3. And we know that weightlessness, what the astronauts experience on the International Space Station, is hard on their bodies, that it causes their bones to soften, their muscles to atrophy, it causes fluid redistribution, appears to cause issues at a genetic level, problems with their eyesight. Now, most of those can be mitigated. So astronauts are exercising all the time. They exercise for hours every day just to decrease the amount of muscle loss, bone loss, and so on. But there's other issues that they, how do you work out the fluid in your eyeballs, right? We're just starting to understand the long-term health consequences of that. And so we don't know right now what are the long-term health consequences of being on the moon, being in this 1/6 gravity. Could very well be that, in fact, 1/6 gravity is all you need. That if you've got that, then that's enough, and a human being can experience their entire life. And as long as they work out several hours a day to maintain their muscles and bones, then they could come back to Earth and they'd be fine. But it might be that there are other, physiological issues that just build up over time, and the human being just can't, we can't gestate embryo. A child won't grow properly in that kind of gravity. Are you going to have your toddler doing weights? Like, it doesn't make sense. So, and it might be that the moon is too low, and then might be that Mars is the same thing. And so, there have been these really exotic ideas for how you might be able to deal with low gravity on the moon or Mars. Like, you could imagine this thing called a gravity train. So there's like a centrifuge, like there's this, or like there's like a ride that you experience where you sit on it, and then it turns like this as it starts to turn, but it's like a centrifuge, right? And so you have to live on Mars, but you're on a train that is constantly moving at an angle. And when you take the gravity of Mars matched with the centripetal force that you experience when you're on this angle, going around this big circle, then it balances out to one gravity, and it feels the same as one gravity. But in space, you just set up a rotating space station. You just have it turn, and you mimic the force of gravity, and it's a much simpler operation, and you didn't have to go into a gravity well. So the reality is that we don't know. We don't know the answer. We don't know if people could live on Mars. Like, there are the plans for building a city on Mars, according to Elon Musk and SpaceX. But we don't know if the human body can handle that. That city is going to actually have to be a train that is moving constantly. That sounds expensive and complicated. So right now we are in this time where we don't know what the future of human space exploration. But in the far future, you would expect that the vast majority will be living in large colonies, rotating with artificial gravity, and they don't live in gravity wells. They go down there for vacations. Gravitron, cyclotron. Yeah, that's the one. Leafbinder, did they ever figure out what the smell was from the Russian transport ship to the ISS? No, we don't know yet. Dr. Kenman, when will we get more pics from JWST? They're coming all the time. I just shared one in the latest Space Bites of the Sombrero Galaxy. There was another one that came out the next day. You can go to the JWST website from NASA, Hubble, and every couple of days they'll share a new picture. Kip Nielsen, what's the latest on Starship development? I saw that Super Heavy is taking a new rover to Titan. So no, Falcon Heavy is the launch provider for the upcoming Dragonfly mission to Titan, and it's not a rover; it's a nuclear-powered helicopter. So that's cool. And so like, what's going on with Starship? Like right now, we are a few weeks after the sixth test flight of Starship. And we're probably going to see more versions that look exactly the same of what we just saw. They're going to attempt to capture the booster, attempt to soft land Starship in the ocean, attempt to relight the engines, maybe attempt to carry a payload into orbit. Things aren't going to get sort of the next big phase of development probably until early 2025, when they're going to probably attempt a capture of Starship itself. And so if they can capture the Super Heavy and they can capture Starship, then those will be the next big development. And if they can do that, then they're going to move towards starting to attempt refueling Starship in orbit. So they're going to do a test of cryofuel transfer in orbit, probably sooner than later. But the long term is that they've got to send the human landing system to the moon. And that's going to require 15 to 20 refueling flights of Starship to fill it back up with propellant so that it can then go to the moon. So you're going to see some, the next big milestones that you're going to watch is a capture of Starship and tests of transferring cryogenic propellants in orbit. C++ universe. If we construct a tunnel on Europa at a depth of 15 feet, will 15 feet be enough to stop harmful radiation due to Jupiter? You don't even need 15 feet. What's that? 5 meters. You just need 1 meter. So if you have 3 feet, 1 meter of water ice between you and space, that will protect you from all the radiation from Jupiter, all the radiation from the sun, and all of the cosmic radiation that's coming from the entire universe. Sorry, just looking at the questions. Kareem Bay Booty, are quark stars still theory, or have we found them? Yeah. So a quark star is this theorized in-between phase of a neutron star and a black hole. And so, when you think about the way stars die, you have a star like our sun will die as a white dwarf star, that it will run out of material in its core to keep fusing. It will blow off its outer layers and it'll just be left as a white dwarf. When you see a white dwarf, you're actually just seeing the exposed core of a star that is now just cooling down to the background temperature of the universe. But if the star is more massive, like 8 to 10 times the mass of the sun, then when it dies, 8 to 20 times the mass of the sun, I forget the exact numbers. Anyway, then when it dies, it becomes a neutron star. And that is because you get this tremendous force, this implosion that's happening of the star, and it smushes the protons and the electrons together, and it creates just this object that is made of neutrons. And that if the star was a lot more massive, say like 20 times the mass of the sun, then when it dies in a supernova, then that implosion, overcomes the neutrons and it turns into a black hole. We don't exactly know what it is. And so it's theorized that there's this in-between stage, that if you get the amount of mass exactly right, then the neutron star will collapse down one more level. And it'll go from neutrons into quarks, which are the fundamental particles that make up neutrons. And the way you would get that is if you had a neutron star that is orbiting around a companion star. The companion star is feeding material to the neutron star. It's increasing the mass on the neutron star, and it hits some number, and then it goes and crunches down one more level, and could give off a blast of radiation when this sort of compactification happens. And so this has been proposed as one explanation for fast radio bursts. These are these weird random blasts of radiation that we see around the universe. It could very well be that we're seeing the formation of quark stars from out of neutron stars, and that is the fast radio burst. There's been some other sort of interesting ideas that people think they're seeing quark stars, but no sort of scientific consensus that says, yes, indeed, we are seeing quark stars. So right now they remain purely theoretical. Christina F54. Christina F54. Which is heavier on Earth, a kilometer squared lump of the moon or a kilometer squared lump of Mars? That's a great question, and I don't know the answer. So let's just quickly find out what is the... So the answer is depends on the density. That what is the density of Mars? And that is 3.93 grams per cubic centimeter. And what is the density of Earth? Sorry, the density of the moon. It's probably closer to 3.34 grams per cubic centimeter. So Mars is denser than the moon is, and therefore if you had a cubic kilometer of Mars, it would weigh more than a cubic kilometer of the moon. It's a fun question though. Peter Kaysen, is someone for real working to exceed the speed of light, or it's pure science fiction? Both are, you could say both things are happening. So, the speed of light is the speed limit of the universe. And according to relativity, that no matter can move through the universe at the speed of light or faster. That only objects without mass, like photons, can move at the speed of light. And that as you attempt to get closer and closer to the speed of light, it requires more and more energy, and it sort of approaches infinity, and you can never reach the speed of light. And these are the laws of physics as we understand them. And yet, people take the laws of physics as a recommendation, as a mild suggestion, as opposed to the laws of physics. And so they are attempting to break the laws of physics as we understand them. And there have been several ideas. One idea is, of course, a wormhole where you have 2 points of space that are connected, and so you go into one part of it and you come out the other side of it. That's a possibility. Do these things exist? Nobody knows. Can they be stable? Nobody knows. There's math, but math doesn't necessarily mean that these things are real. The other possibility is a warp drive, where you are not attempting to move through space itself. You are attempting to compress space-time in front of you and stretch space-time behind you. And in theory, you don't move. It's space that does the moving. And in theory, space-time can be distorted and stretched. The most famous idea of this is known as an Alcubierre drive, named after the physicist who sort of did the math to show that this might be possible. But it requires something called negative energy, which is a thing that doesn't exist. So, if you can have negative energy, then you can have a warp drive. But we don't know whether we can have negative energy at all. And so, it violates the laws of physics as we understand them. People have proposed ways that it might work, but nobody has found any practical way to make any progress or headway at all in that direction. And then you sort of think about the observational things that we see, which is that we don't see a universe where people are flying their warp drives around. That, we are limited in how quickly we can get to other star systems. And we would expect that other civilizations are limited in the same way because they are trapped within, the speed of light and them trying to be able to go other places. That, maybe one of the reasons why we don't see any evidence of aliens out there is just it takes so long and it's so expensive and so difficult to travel from star to star. And that if there was warp drives, then now being 1 trillion light years away from Earth doesn't matter. You turn on your warp drive, a quarter of a second later, you've traveled 1 trillion light years and here you are. So why don't we see all of the warp drive aliens flying around? So it might very well be that one of the reasons why we don't see any advanced civilizations out there in the universe is that it is physically impossible to travel faster than the speed of light. That no matter how hard you try, you will never be able to solve this problem. And we have to be just okay with that, right? I know science fiction has said that traveling faster than the speed of light is easy. You just hop in the Enterprise and you turn on the warp drive and away you go. But it might not be like that at all. Dougal, would the top layer of Enceladus be radioactive from Jupiter? I'm assuming you're talking about Europa. Would the top layer of Europa be radioactive from Jupiter? So no. The radioactivity that comes from the solar wind, that comes from cosmic rays, that comes from trapped radiation in Jupiter is because of the speed. It's because you've got these particles. In many cases, they're just protons. They're just atoms of hydrogen, right? Or maybe heavier elements, all the way up to maybe iron, that are traveling at close to the speed of light. And when they go through your body, they do damage to your DNA. But if you slow those particles down so that they're no longer moving fast, they don't do any damage. And so it's not like they are when they hit water and they are breaking apart the water into hydrogen and oxygen, they're not leaving behind some kind of radioactive residue. It's very different from radiation from something like a chunk of plutonium, which is constantly putting out gamma radiation and alpha particles, and these are causing damage to your body. But with cosmic rays, they are just an atom of hydrogen that is moving at very close to the speed of light. And so you wouldn't get this radioactivity in that first meter of the ice on Europa. And you could drink, right? If you we always talk about this idea that you surround your spacecraft with a layer of water, and that could be your reservoirs of your water. You drink the water that's protecting you from the radiation of space. Raj Luther, we've seen ideas for O'Neill cylinder and ring-shaped artificial gravity structures. What about other shapes like a sphere? So the problem with a sphere, like if you imagine you have a sphere that is floating in space and then you want to have artificial gravity in that sphere and you rotate the sphere, well then on the equator of the sphere, you're going to have the gravity that you want. But then as you go a little up from the equator of the sphere, then the gravity is going to go down and you're going to be kind of tilting a bit to the side. You're going to be sort of push towards the equator of the sphere. And of course, if you're standing at the very top of the sphere, you're going to be experiencing no artificial gravity. You're going to fall, and then you're going to fall down to the other side, and then you're going to sort of oscillate in, and you'll end up somewhere in the middle of this rotating sphere. And so the trick with the O'Neill cylinder, the trick with the ring, is you make the whole structure that you are attempting to walk on, where the artificial gravity is perpendicular to the axis of rotation. So any place that you would want to walk, this is going to have the artificial gravity. So this is the shape. It has to be a cylinder of some variety, of some length, either a very thin ring or a very thick cylinder. Whatever it is, it has to be a rotating cylinder. Omni-light. If we do discover things that are faster than light, what kinds of doors to science does it open up? I mean, if we can discover practical faster than light travel, then it opens up everything. Imagine if you wanted to understand what was happening in Europe, and the only way you could understand what's happening in Europe is that you could point your telescope at Europe. Or you could listen to letters written by people who have been to Europe. You could read letters and descriptions of Europe. That if we could actually travel faster than the speed of light, then we could go and explore places around the universe as easily as we explore places on Earth. We could go to the moon. We could go to Mars. We could go to Andromeda. We could go to galaxies that we are now seeing 10 billion light years ago. We could just go there. We could catalog various planets in the solar system. We would understand the history of the universe in a different way, or at least we would understand the present nature of the universe if we could travel faster than the speed of light. Astronomers are really lucky that light takes time to get to us, because it really is sort of a time machine, that the farther we look out into space, the further back in time that we're seeing. But the downside is that you don't get to see what things are happening right now. When we see a galaxy where the light has been traveling for 10 billion years to get to us, then we're seeing how that galaxy looked 10 billion years ago. Well, imagine you could do both. You point your telescope at the galaxy, you look at it, you see what it looked like 10 billion years ago. You then hop in your faster than light drive, you move towards that galaxy, you pop a billion light years closer, look at it again, see how it looked 7 billion years ago, and then you hop in it again, and you just get closer and closer and closer, catching up to how it looks today. It would be incredible, game-changing. Everything would change. So, when I say that faster than light travel is probably never going to happen, that's not the answer that I want, right? I don't want to destroy sci-fi Christmas. I want us to be able to travel faster than the speed of light. That would be the best thing ever. I want to live that Star Trek future, but I've made peace with the universe that we appear to live in, and not the universe that I want us to be living in. And you need to do the same. Or don't, whatever. I'm not your dad. Russell Breyer, would your bread be considered a life form if found on Mars? Absolutely. There would be bacteria crawling around on Mars. Now, the bread isn't alive, but the bread would be covered in bacteria and yeast and mold and other organisms that you don't want to think too much about when you eat a piece of bread and what's actually in the bread that you're eating. but so it's not alive, but it is evidence that it contains organic materials, it contains interesting chemistry. They've been mixed together in different ways. And so, yeah, I mean, if a loaf of bread was found on Mars, it would be evidence of life. It would be containing life, but it also would be evidence that, you wouldn't get that naturally. Arjone, I heard Earth was the densest planet. Correct me if I'm wrong. No, you're correct. Earth is the densest planet. Earth has a higher density than Mercury and Venus. And in fact, Mercury has a higher quantity of heavier elements in it. Mercury has more metal than the Earth does, but Earth has more gravity, and so it crushes down the material inside itself tighter. And so even though it has a lower sort of amount of metal than Mercury does, it has a higher density, and that's just due to the mass and the compactification of the material. Where are we at? Okay. Jimero NT, is it more likely to have life in a planet as opposed to on a planet? This is an open question that we don't really know the answer to right now. We find life anywhere on Earth that we find liquid water. And so scientists have found life floating high up in the atmosphere, completely held aloft, living on droplets of water that are floating from continent to continent. They've found life at the bottom of the ocean, underneath ice sheets in Antarctica. They found life in pools of hot water at Yellowstone. They found it in nuclear reactors. They're cooling pools. And then they found it underground. They found it relatively close underground, but they've also found it like as far down as you can go, 10 kilometers down. If you have liquid water, you find that there's some kind of life. Now, it's not going to be trees and ferrets and people, it's bacteria and archaea and other extremophiles, but it's down there. And so there's one perfectly reasonable line of thinking that in fact, when you count up the total biomass on planet Earth, there's more life under the ground on Earth than there is on the surface, which is mind-blowing. And so when we think about the kinds of places around the solar system where, if we take that same thing, wherever you find water, you find life. If we go to places like Europa or Enceladus or Pluto or Eris or Sedna or Planet 9 or whatever, then you are going to find liquid water on those worlds underground. And so if there is life on those worlds, it's going to be underground. And if indeed the vast majority of the life on Earth, the biomass on planet Earth is in between the rocks in the hot water, it's fed by geothermal activity. We see that on other places. We see that on Venus. We see that on Mercury. We see that on Mars. It could very well be that there's life on all of those places. So we have really scratched the surface for where there could be life in the solar system. And it's really interesting because while the surfaces are very different, it could very well be that the subsurfaces are very similar, that you've got geothermal energy that's keeping you warm, you've got access to liquid water, you've got various chemicals that are contained in the rocks that provide the bacteria with food, that we know that over time there have been meteorites passing from planet to planet, world to world. We found meteorites that come from Mars, from Vesta, from the moon here on the surface of the Earth, and it could very well be that material has just been going from planet to planet, world to world, moon to moon throughout 4.5 billion years of the history of our solar system. And life has been able to make its way into the cracks and crevices, live underground in the places that are safe. And so it could very well be that there's an enormous amount of life across this entire solar system. It's just up to us to find it. And it might also be that there's none. It might also be that we are completely alone, not only here on planet Earth, but in the galaxy and maybe even the entire observable universe. This is an unknown question. You live in a time where we don't know the answer to this question. And you will probably be alive when this question gets an answer, either that we find life on Mars, that we find life on Europa, that we hear a signal from an advanced civilization, that we detect the presence of a civilization that is polluting its atmosphere with chlorofluorocarbons, or you live in a time when the sphere of the observable grows to the point that, mathematically speaking, the universe is probably alone, that we have failed to find any biosignatures 100 light years away, 1,000 light years away. And we've looked very carefully, and it starts to feel more and more like we're alone. So, yeah, interesting. If my beard was on Mars, would it be life? Yes, of course. It's filled, like, it's even grosser than what than what's in bread, probably. Mites. Are we on to the next page? Not quite. Okay. Born, Mr. Man, born too late for the age of sail, born too early for interstellar travel. Yeah. There's always, like, no matter when you arrive on Earth, there will be a time that questions that have puzzled scientists for thousands of years will have been answered. And yet there will be questions, exploration to be done in the future that we won't live to see. Imagine if you went back and you could talk to Galileo or Aristotle, and they would have these questions about how the world works. And, you as a scientifically minded person would have a lot of their answers. Like, how does the sun work? Oh, well, the Earth is, the sun is a star like all those other stars, and the Earth rotates around it and orbits around it, and the other planets are like the Earth. Whoa! Why does it make fire? Oh, well, it's got fusion in the core. When you put hydrogen, helium, hydrogen together, it turns into helium, and that produces gamma radiation, and that produces energy, and that's what we see. Whoa! Right? And yet, you could sit down with the astrophysicist of the future and be like, did you guys find life? What is dark matter? What is dark energy? Why is there more matter than antimatter in the universe? What's inside the event horizon of a black hole? Like, the questions go on. And I'm sure, that future astrophysicist would have questions for their future descendants. So I think everyone will feel disappointed that they weren't born at the right time, but there is no right time. Here you are sitting in Europe or wherever else you might find yourself, watching a Canadian who is streaming information about space and astronomy from his computer. I don't have a broadcast studio. I just have a camera and a computer, and that's and the internet and YouTube. And you're able to watch this kind of information. And I didn't have to go to some broadcast company and ask them if I could produce a television show. I just did it. So, yeah, it will never get old to me, the wonders that we live in and the crazy things. With AI, like, yeah, it hallucinates, but you talk to a computer and it answers. It's crazy. So Russell Breyer, his actual question was, if an entity was on Andromeda somewhere, would their observable universe be different? So Andromeda is 2.5 million light years from Earth. And if you were on Andromeda, then you would see roughly the same observable universe that we see. You would see, but instead of seeing Andromeda in the sky, you would see the Milky Way in the sky. You would see very different stars because, the stars that we see in the sky are the ones that are within just a few hundred light years of us. And so a person somewhere in Andromeda would not see any recognizable constellations, but they would see the Milky Way. And they would also, but what they would share is they would see M33, the Triangulum galaxy, which is the other big galaxy in the local group. they would see the Milky Way surrounded by the large and small Magellanic Clouds and other dwarf galaxies in the way that we can see Andromeda has its own dwarf galaxies. But then things would start to look very familiar. They would see roughly the same galaxies in roughly the same positions. The only difference is that they would see a version of the universe, their observable universe would be 2.5 million light years, or I guess 2.5 million years less time in one direction and 2.5 million years more time in another direction. So they would see just a slightly different part of the universe than what we see, but roughly it would be the same thing. So I'll do one more question. And then, but I got to do a meeting. So, Robin, how is your fascination of space science resonating in your family? Well, I'm really lucky because I come from a family that is very space science oriented. So my parents were really into astronomy, science fiction. They took me to go see the Star Trek movie, the Voyage Home. No, the first Star Trek movie, when it was in 1970. I think I was 7 years old. Freaked me out, but they loved it. And we watched Star Trek as when I was a kid. They went and took me out to see meteor showers. They bought me books because they could see that I was really into space and astronomy and dinosaurs and things like that. And so they supported that quite a bit. My father watched the moon landings when he was a child, and so when the first launch of the space shuttle happened in 1981, he was quite excited about it and woke me up to watch the launch with him. He still watches the live streams from the International Space Station. He calls them the floaters. He'll send me a text message like, "Oh, Fraser, the floaters are on." I'm like, "Oh, okay, yeah, they're doing a spacewalk right now, Dad." He's like, "I know." So, he has his own telescope. He's quite active on the internet. He's a photographer by trade. My mom passed away, but was very into science fiction. They went and saw the Alien movie. I remember them coming back from watching Alien and being freaked out, but they loved it. Took me to 2001 when I was a kid, and it was too soon. I was really scared by that movie. It haunted me. Only recently I watched it and was able to kind of tough my way through the movie and enjoyed it. My kids are very into science fiction, fantasy. They don't really care that much about space, but if I say, "Hey, there's an aurora, do you guys want to go see?" and we'll go together and we'll go watch the aurora. Or if there's something interesting I'll set up my telescope and invite them to, they're adults now, but I'll invite them to come and look through the telescope. My wife is very into space and astronomy. She was more into nature before we met, she's a macro photographer of insects. And so I've sort of gotten more interested in biodiversity and life and things like that. And she's gotten more interested in space and astronomy, but she was reading about space and astronomy before we even met. I don't know anybody. I know one person in my sort of wider friend community who seems skeptical that humans have gone to space. And so every time we talk, she's like, I don't understand how we could be on the moon or how we went to the moon. I'll explain it, and she's like, I just don't get it. I don't like it. So whatever. But yeah, I think the thing that I love about space is that everybody loves space, right? You can have different political leanings to somebody else, but if you want to talk about space, chances are you wouldn't be able to figure out what their political leanings are. They're fascinated by pictures from the James Webb Space Telescope. They're fascinated by news about the exploration of space, that they loved the pictures and the stories that happened. They love science fiction. Space is this thing that connects us, and hopefully it will be one of the last things that will get deeply politicized. I know there's a lot of trolls and anti-science people out there, but mostly we can easily ignore them and just talk about this thing that we love. So So hopefully you all have a very similar thing. You have varying levels of support around you from your friends and family on this thing. And even if they're not as into it as you are, you show someone a cool picture of Saturn from the Hubble Space Telescope and they're into it. And so I think we're lucky that we have an interest that most people share. All right. Well, how did we do? We were 427 people are watching the stream right now. And compared to, this is crazy. So compared to normally when I do the Pacific time stream, it was like 600 people. So with this being like the first time that I've ever done this, mostly unannounced, didn't really provide people a lot of contextual information. I'm shocked that this many of you were found your way to the feed and are watching it, and so this has completely validated the European experiment, because I was pretty nervous. I thought, okay, I'm going to do this stream and nobody's going to show up and we're not going to get great questions and I'm going to have to shut the thing down early. But no, this went great and I'm really glad. John Suffield, thank you for moderating this time. I think it was great. Hopefully this gave you one week where it's easier to do the job. But a huge thanks to the moderators who are helping out with this feed. It means a lot. You will see this chopped up and in the question show feed in the coming weeks. All right. Thanks, everyone. And we will see all of you next week.